The term hardness has a specific meaning in engineering. It is the resistance to permanent penetration. A steel ball pressed into a piece of lead produces a spherical indentation. A specific amount of force is used. Resistance to penetration is measured either by the depth of penetration or by the residual area of the indentation. Such measurements, combined with the magnitude of the contact force, can be used to calculate a hardness number. Two common tests for quantitatively evaluating resistance to penetration will be examined next. The Brinell hardness tester uses a specified load to force part of the lower surface of the 10 millimeter diameter hardened steel ball into the test material. The penetrator is brought into contact with the specimen. The load is applied hydraulically, held for 30 seconds, and then released. A spherical indentation results. A special microscope is used to measure the diameter across the top of the indentation. The Brinell hardness number is then calculated by dividing the applied load, 3,000 kilograms in the standard Brinell test, by the spherical area of the residual indentation. This area can be determined from the diameter of the indentation, small d, and the diameter of the steel ball, capital D. Commonly, however, the area is not calculated. Instead, charts are used to go directly from a measured diameter to the corresponding Brinell hardness number. Brinell hardness numbers have the same units as stress, load divided by area. For metals, the Brinell hardness number ranges from about 100 to 600. The conventional Rockwell hardness tester indicates resistance to penetration directly on a dial gauge, which measures the depth of penetration of especially shaped penetrators when pressed into the test material under a particular load. Depending on the resistance of the material to be tested, forces of 60 and 100 kilograms are used with a 1/16 inch diameter hardened steel ball penetrator, affording Rockwell B readings, and for harder materials, 150 kilograms of load with a diamond-tipped conical penetrator, affording Rockwell C readings. We shall determine the Rockwell hardness of certain steels. The diamond-tipped cone penetrator is inserted into the machine. A small cylindrical specimen of ASTM 1045 steel with a carbon content of 0.45% will be tested first. The specimen is brought into contact with the penetrator. A 10 kilogram minor load is applied to hold the material and penetrator in contact. This is accomplished by tightening a hand wheel until the dial indicator reaches the set mark. The major load of 150 kilograms is applied when the load lever is tripped. The dial gauge is marked to subtract the depth of penetration from an arbitrary value so that a softer material yields a lower reading than a harder one. When the load is removed, the dial gives the reading directly. In this case, C13. The specimen has been indented by the cone. The indentation is quite small. A similar test is performed on ASTM 1095 steel, which contains 0.95% carbon. Here, the hardness number is C30. For a softer material, the diamond cone would penetrate beyond the reading capability of the instrument. Hence, the 1/16 inch diameter ball-tipped penetrator is used analogously with a 100 kilogram load. The hardness of this ASTM 1020 steel specimen with a 0.2% carbon content will be read on the B scale. Its Rockwell hardness number is B80. We see from these tests that higher carbon content is associated with greater hardness. The tensile strength of these materials have also been observed to increase with carbon content. Brinell and Rockwell readings may be compared on a chart. These hardness numbers are different and are not linearly related. Readings on the Rockwell B and C scales may also be compared to each other. It is seen that a hardness of 100 on the B scale would correspond to a hardness number of 20 on the C scale. Materials with a greater tensile strength also exhibit greater hardness. Domer has found that the tensile strength of materials is approximately 500 times their Brinell hardness number. Hence, a hardness measurement can be used as a rough estimate of tensile strength. There are several other hardness testing methods. Among them, the Mohs hardness test for minerals is based on a scratch test. The harder material, in this case diamond, is able to scratch a softer glass plate, though glass is a comparatively hard material. On the Mohs hardness scale, the softest material is talc, number 1, and the hardest, diamond, is number 10. The Mohs scale may also be compared to the other measurements. The scratch test measures abrasive hardness in addition to indentation hardness, and hence another nonlinear relation between hardness numbers results. Another mechanical property frequently measured is ductility, which is defined as percent elongation to fracture. Some materials are ductile when pulled slowly, but brittle under a dynamic load. Furthermore, a material that is ductile at one temperature may become brittle when it is cooled to the temperature of liquid nitrogen. In a static tension test, toughness was measured by the modulus of toughness, the area under the stress-strain curve. It indicated the amount of energy absorbed in deformation and fracture. For materials of comparable strength, toughness and ductility are closely related. Dynamic toughness is measured in impact testing machines. A heavy pendulum has potential energy proportional to the height to which it is raised. When allowed to swing, potential energy changes to kinetic and back to potential energy. If the pendulum rises to its initial height, there is no loss of potential energy. Energy loss is measured on this dial. When a piece of steel is inserted into the path of the pendulum, the energy required to break it will be registered as a loss of potential energy, and the pendulum will rise to a diminished height. This energy loss, as indicated by the dial, is measured directly in foot-pounds. The energy loss, like the modulus of toughness, is related to ductility. Some materials, such as this SAE 4140 steel, do not break under a single impact. In an impact test, the total energy absorbed to fracture is desired. But this specimen did not break. Specimens are therefore notched. In addition to producing a stress razor, the notch concentrates the energy at a narrow region. A notched 4140 specimen does break. Bending impact specimens may be either simply supported, as in the Sharpie test, or cantilevered in IZOD machines. The size of the specimen, as well as notch geometry, are standardized. A notched SAE 4140 steel specimen, when tested in the Sharpie configuration, breaks. The energy absorbed to fracture is 8 foot-pounds. The fracture surface is rough and relatively flat, typical of brittle failures. Steel is a material whose toughness may be improved with certain types of heat treatment. The fracture surface of the heat-treated 4140 steel exhibits shear lips on the sides and a rough, horizontal fracture region in the middle. Shear lips are a sign of high ductility. Ductility and toughness are temperature-dependent properties. We shall retest our heat-treated 4140 material at various temperatures. A thermocouple is attached to the specimen in order to measure its temperature. After a liquid nitrogen immersion, the specimen is inserted into the impact testing machine, and its temperature is allowed to rise. When the temperature reaches a specified level, minus 170 degrees Fahrenheit in this case, the pendulum is released and the energy absorbed, 20 foot-pounds, is recorded. At minus 250 degrees Fahrenheit, the energy absorbed is still lower, 12 foot-pounds. The absorbed energy can be plotted against the test temperature. It is low for low temperatures, but eventually a sudden increase is observed, beyond which the curve flattens out again. The behavior of the material has changed from brittle, low energy absorption to ductile, high energy absorption. The temperature at which this change takes place is called the ductile-brittle transition temperature. Hardness and impact test, because of their simplicity and because specimens for them are relatively inexpensive, are frequently used for the purposes of quick comparison of materials and for quality control procedures.
Oh man. Oh man. That was awesome. Sometimes I start the show with a film that I think is a little too niche, a little too esoteric, a little too procedural, but I love nonetheless. I mean, there's so much to love about this film, and not to mention the giggling, the immature giggling with load, penetrator, etc. And all the devices and all the scales. Oh man, this is why I collect films. Really, watching some of these really just, if you're a mechanical engineer, this is great. or a chemical engineer, but you know, the average layman will never, ever, ever think about these. Although, it's interesting to see how some of these tests have made their way to YouTube in things like Will It Blend, and like we take this object and we put it in a in one of these vices. How that has become like a thing, a genre. So here it is, back 1975. I'm Skip Alzheimer, and welcome to the AV Geeks Lunchtime streaming show, where we watch old 16mm films. And this was something that we actually had on 16mm. Almost everything we show, we have on 16mm. Some of them we've already pre-scanned. Some of them we scan on demand, and you get to see it live. It goes straight from this machine right here, and then it makes its way through a series of tubes into your eyes. And your ears. So thank you to all the technology that lets us dabble in things like that. All right, well, now it's time, speaking of tubes, to learn about brass choirs. Enjoy.
No symphony orchestra would be complete without all of its choirs. In the broad sweep of emotions, the versatile strings are indispensable. The woodwinds, among other contributions, are unexcelled in portraying the pastoral. And so too the brass instruments have a major function. That of assisting in the sweep up to great climaxes and crowning them, as was demonstrated in the selection you have just heard. As is the case with all other choirs of the symphony orchestra, the brasses are represented by soprano, alto, tenor, and bass. I will now introduce the trumpets, the sopranos of the symphony brasses. The trumpets are brilliant, military, and dramatic. The alto of the brass choir is the French horn. The tone quality of the French horn is mysterious and romantic. The trombone. The trombones are usually the tenors of the brass choir. But there is also a bass trombone. The trombones are powerful, noble, and sonorous. And now the bass of the brass choir, the tuba. The tuba represents massiveness and power. The brass choir will now play for you the march from Tannhäuser.
So that film was from the Mogul Brothers collection and was an early Irpy film, and which eventually got purchased by Encyclopedia Britannica, and so then they re-released it. But what's interesting is the Mogul Brothers collection was a library, film library in New York City, and sometimes they would just tack things on, and so at the end you have the end, and it's a spider web, which is pretty great. And this was a great film anyways. It's kind of wonderful. And I think there's 3 different versions of it, and I think we scanned the second version of it for this Encyclopedia Britannica project we've been working on. Anyways, this next film is an interesting promotional piece for the Army Corps of Engineers. And what I love about it is it's a presentation within a presentation. And so this is We Were There. Enjoy.
Have a nice weekend. Class dismissed. Oh, good paper. Very nice. Good luck on the game, boys. Oh, Becky, Carlos, Gary, and Linda, please stay a moment. Captain Keenan is going to come by to help you on that special project. If you want to go to the workbench, you should be here anytime.
Good afternoon.
Great, right on time. This is Captain Keenan, who's been good enough to come by today to answer your questions on the Army Corps of Engineers and what its role has been and is in the management and development of our country's natural resources and in the protection of our national security. Captain, this is Becky, Carlos, Gary, and Linda.
Mrs. Drake has sort of filled me in on your project, which has to do with our country's 200th birthday and how the Army's Corps of Engineers has helped to develop, build, and protect America in these various roles. Well, I've had to do my homework, too. And to help me help you, I've brought some film and other pictures along. By putting it all together, I hope to give you an overall picture as to what the Army's Corps of Engineers has done and is doing for our country. Now, where would you like to start?
Well, I always think of the Army as marching and fighting war. But engineers build things and prevent floods from happening.
I read where you build dams and control our big water ports like New York.
But you're still soldiers. I mean, like back in World War II, Korea, and Vietnam, right?
Whoa, yes, no, yes. I mean, you're all partially right. But an Army engineer, military or civilian, he's a special breed of cat. We wear 2 very important hats in our jobs. Well, just like the one you mentioned, Gary, we do have a proud combat history going back to the Revolutionary War. But Army engineers have also made important contributions to America's growth, from helping to explore our own country to helping space exploration, from building historic forts to major structures in our nation's capital. We are soldiers, for sure, but we're also pioneers, architects, builders, and innovators, and always American citizens who care.
I'd like to hear the captain tell it his way, like from the beginning. Does that turn anybody off?
Okay, let's try it that way. But first, I need to show you who it was that got this whole story started. Carlos, would you put that on the projector, please? None other than George Washington, engineer, soldier, statesman. While still a general in charge of our Continental Army, he was authorized by our then Continental Congress to set up a special department to be headed by a chief engineer and 2 assistants. So the history of the Army Engineers, which began the day before the Battle of Bunker Hill, is actually longer than that of our own country. Military engineering efforts during the Revolutionary War were confined mostly to building defensive fortifications to protect our forces and garrisons against British attacks. The job done was pretty good for the time and the limited experience of those involved. The creation of a Corps of Engineers was actually accomplished by Thomas Jefferson, who as president persuaded Congress to establish a military academy. This country's vast interior began to itself, thanks to pioneers like Major Law, but not for conquest. An important milestone in the Corps' role of helping to shape America's destiny occurred, as was transportation of mail. And by this act, Army engineer officers could be used in the carrying out of work as well as civilian engineers. It was this act which really established the Corps' Civil Works program as we know it today. It meant Army engineers would have two roles of national importance. One, of the Chesapeake and Canal, beginning in what is now Georgia, ending to Pittsburgh, before this ambitious project was suspended. But Corps Civil Works projects continued, and by 1827, engineers were to become directly involved with the engineering assistance to help develop and build the first railroads. More were to become civil. With the surge of railroad, new horizons and opportunities, passages through the delta where river opened to sea. Progress to make them is sometimes failing, but mostly succeeding. A brilliant West Point graduate, Robert E. Lee, devised a system which forced the river to do the job of scouring the channel clean. Two engineer officers named management, which today is the science of river hydraulics. In the Great Lakes region, a stubborn natural rapids at a point called Sault Ste. Marie was a barrier which had to be conquered if this 1,000-mile-long shipping route was to serve our expanding waterway commerce system. Army engineers' involvement to change the Great Lakes into a servant for those who would sail these lakes and benefit from their man-made improvements. Between 1842 and 1846, the legendary explorations of Lieutenant Fremont and his Kit Carson extended into what is an area for exploration and survey. So Army engineers were sent west to discover what was out there, what the land people living there were like. Among the made in California was gold, and that would immediately create a stampede to the west. The Pacific Railroad Survey fell to Army engineers who recommended exploration and surveys covered California, Oregon, Utah, the Rockies, land which was barren, unfriendly, and challenging. But what was learned from these early studies meant opening the West to those who would come this way in increasing numbers to settle in America's western frontier. Any of you have any questions or comments at this point? I'm here to help you, you know. Well, sure, Gary, go ahead.
Well, like you guys were building all these railroads and canals and things. But didn't you have to fight it all? I mean, like in war?
Yes, Gary. Army engineers, being soldiers, know what combat is like when our country's security is in danger. Army engineers were there during the war with Mexico. Among them, men named Beauregard, Meade, McClellan, Lee. Names destined to fill pages of American history during years not far away. But in the war with Mexico, they helped prove that Jefferson's vision about West Point would prove to be correct. They were men of exceptional engineering and soldiering ability.
What about the Civil War? Did the engineers fight? And for which side?
Good question, Becky, and one which requires some explanation. Just before our Civil War began, Washington, D.C. was the scene of intense Army engineer activity. We were planning the completion of the Washington Monument, beginning the dome for our Capitol building, planning civic improvements for our capital city. President Lincoln was in office, hoping for a solution to the problems which were splitting North and South. But as you know, that was not to be, and Civil War resulted. Even our Army couldn't overcome personal feelings. Some followed their convictions by joining the Confederate Army, which included General Beauregard and its distinguished leader, Robert E. Lee. For engineers wearing both uniforms, the war introduced new combat applications, like the use of telegraphy for faster communications, employment of aerial balloons for observation. These two military experiments really helped lead to what became the Army Signal and Air Corps. On land, both sides used railroads to their advantage to move men and equipment where they were needed. Our Civil War not only changed the country, but also the way war would be fought in the future. So it was both a trying and testing time in our history. When the Civil War ended, Washington, D.C. needed attention. Population increase had made streets a nightmare. Conditions were so bad that some people wanted our capital site moved elsewhere. But Army engineers were put to work, finishing what had been started, laying out the grounds for Arlington National Cemetery, paving streets, and in so doing, setting the stage for their future involvement in design and building, which would make Washington, D.C. a national showcase. As the 1800s moved on, civil works projects again focused on our rivers and harbors, and Army engineers were at work developing navigational systems to extend our waterborne transportation routes. In the West, exploration was beginning to reveal the still blank spots on our country's map. Areas like the upper Yellowstone Valley. The efforts of Army engineers to map and bring back reports about this unknown area resulted in the creation of what is now Yellowstone National Park. For its first 10 years, this natural scenic wonder was victimized by neglect and man-caused abuses. Aware of what man could do to destroy Yellowstone, the Corps of Engineers asked Congress for authority to build roads and establish Army patrols to preserve and protect the park. In the mid-1880s, Congress authorized the request, and an Army engineer captain, Dan Kingman, who would later become Chief of Army Engineers, spent a 3-year tour of duty in Yellowstone, during which he laid out a highway loop which is still a main artery in the park's roadway system. The concern of Army engineers about protecting and preserving land areas in our West wasn't limited to one place. Yosemite in California was another, and it too was kept safe from exploitation and abuse by Army engineers before our National Park Service was created and took over the job. As fast as America was growing, so were her transportation needs. Old Man River, the Mississippi, was still a stubborn challenge, which required engineering work to safeguard shipping and passage along its winding course. The Arkansas and the Missouri rivers also posed monumental problems, which received Army engineer attention to make them navigable and safe for the people who lived close to their banks. The Ohio River was yielding to navigational development and a real beginning to what would eventually mean a system of interconnecting waterways scattered throughout the country. Harbor improvements were continued by Army engineers in our port cities to better handle ship traffic. When the 20th century came along, Army engineers had already provided 125 years' service to their nation and had been a dominant factor in its growth and protection of...
That film was kind of beat to hell. For there to be so many splice breaks in the middle of it tells me, I don't know if somebody rewound it and something broke, or they didn't have a good loop on it, so it was just tearing sprockets periodically. Like, it's weird. Normally it's at the beginning or the end that you see that those like multiple splices because of rewinding or whatever, or they didn't thread it right. But in the center is kind of weird. So unfortunately, sorry. All right. So behind me, I have another film on the scanner, and somebody asked the difference between this and the older machine that I had, which was the German flash transfer, made by a company called NWA Nova. That would only do 16 millimeter, and it would only do SD, and we had a box that would upconvert it to HD, then we would broadcast it. This Blackmagic Syntel is made by was originally made by a company called Rank Syntel, but then the technology got bought by Blackmagic, and they sat on it for I feel like 8 years to try to come up with a new machine that used a camera instead of a flying spot CRT to scan the film. And so Blackmagic was making cameras, and so that's what they put in here. And so this machine can do up to 4K 35 millimeter and 16 millimeter, and it also has what we call video tap. It has a HDMI out, which we plug into a box, which we plug into here. So what we can do is I can be scanning a high quality file on this computer behind me, and then I can also be pumping video and audio out via the HDMI for the stream. So most scanners can't do that, and so this one is pretty great in that regard. So this is why we're able to broadcast. All right, I geeked out pretty hard there. So anyways, this next film that we have set up is a child development film, and these tend to be like nature documentaries in that, let's watch the child do this and let's watch the child do that, and then there's this kind of raw footage of whatever's going on. So I haven't seen this one. I'm not sure what it's going to be in it, but I'll be standing by in case it gets crazy, like too crazy for YouTube. All right, anyways, here's Half a Year Apart. Enjoy.
This short film shows two children, 6 months apart, in a concentrated 45 minutes of playing. This is Rachel, age 2. For her, play is a chance to explore through her senses. This is Josh, age 2.5. For Josh, play is a chance to build events. Play is always a chance to explore. It's only how we play that changes.
Oh! Like I said, I had not seen this film before, and I had a guess that it was going to be like that. And I was not disappointed. It's fascinating to see some of you in the comments embrace films like this, and some of you are like, ah! Even wanting to invoke a clown. That's hilarious, John. That is so hilarious. Don't careful what you wish for. Yeah, so that's the one thing about AV Geeks. I will show you stuff that you probably had no idea that you would be seeing. And so I'm happy to do that. This next film is a whacked out Encyclopedia Britannica film about time. Enjoy.
$100 million, $200 million, $500 million, $750, $1 billion years, $1 trillion, 1,000 years, 100 years, 25 years, 1 second, a microsecond. No time but the present time. No memory of the past. No expectation of the future. Three dimensions in space. The fourth of time, not yet perceived. What is time? An appearance which takes the form of motion, of day and night, of play and sleep, of being, of life. Perhaps life is time. And the days, the minutes fly fast, unseen. We move through time. We live in it. We say that time is money, that time is precious, that time is king. We know what can be pressed into a week and into a busy day. Awareness of time experienced by the perceptions of man, by the pace of events, by productivity. And yet, what is time? Is time one's view of it? Is time what one does with it?
58 and 10 seconds.
Today I'll be in conference. Try to change employment till 9
And the
o'clock
total
tomorrow.
time will be
400 degrees, 30 minutes.
58
No more than 30 minutes.
and 20 seconds.
Be here on the 14th. Today is the 17th. I've got contractors on my back.
And the
There are
total
6
time will
bulldozers
be
waiting to get up into the...
58 and 30 seconds.
Is time real? I am, and thus time is. But I also wonder why the clock of life is wound but once, and why no man has ever had the power to tell just when the hands will stop, whether late in life or whether at an early hour. Now perhaps is the only time I own, to live, to love, and as I must, to toil, placing no faith in tomorrow, for the clock may then be still. And time flees from my hands like sand in the wind. My past is what I can remember. My future? It defies the imagination. Legends and beliefs have made it simple. It is said that the light was called day and the darkness night, and the evening and the morning were the first day. My day is but a moment in the breath of the universe. Still, I yearn for the promise of immortality. For I am I, and my soul denies the timeless oblivion of death in the dark oceans of a vast eternity. Is time real? Does it have a beginning? Will it ever end? I witness in my life the existence of I do not know what.
sensed the existence of time. He observed, and he could predict summer and winter, planting and harvesting. We apprehend time only when we have marked motion, so Aristotle said. Not only do we measure the movement by the time, but also the time by the movement, because they define each other. Events, their duration, their repeating patterns were perceived in the rhythms of the heavens. Rhythms, time, the seasons, the years, months. The passage of centuries preserved in a few inches of sedimentary rock. Clocks of nature. Time has left behind fine traces of its passing, chronicles of millenniums, of seasons. Moisture makes the tree rings grow wider. Drought keeps them narrow. And a calendar of events can be traced back through time. A year-by-year countdown to date the past. Events recorded in sequence before or after another event, reaching back past the beginning of the first calendar. Stonehenge, 500 years before Christ, perhaps among the first of the calendars. Men set stones in a precise order to identify the summer and winter sun, and to recognize the fall and spring equinoxes. In time, and all are affected by it. So it should be easy to measure time by units, and the counting of time must thus begin at 0. Sand flowing at different rates begins at 0 time. Then it marks the quarter hour, the half hour, the hour. A 17th century pocket sundial counted the same units of time in a different way. And so did years, in their more controlled, more precise manner. 0 revolutions, then 1, 2, 3, tick by tick to the hour. As inevitably, the hands of the clock moved again to 0. Man has learned to break up the apparent flow of time with clocks, each ultimate in perfection, to split the seconds, to count, divide, and conquer time. Still, a tenth of a second has become a precious commodity. In 6,000 years, this cesium clock will not gain or lose more than 1 second. And that second is defined by the vibrations of atoms of cesium-133. The Earth's rotation no longer serves for accuracy. It loses 3 seconds a year, some years. 3 seconds out of 31.5 million seconds. Yet, man seems no closer to defining the entity that is time itself. He may stop an event in each of its positions,
But what would happen if he were able to play with time and change the order of events to suit his own will? Can the clock move back?
Let the word go forth from this time and place to friend and foe alike that the torch has been passed to a new generation of Americans born in this century, tempered by war, disciplined by a hard and bitter peace, proud of our ancient heritage, and unwilling to witness or permit the slow undoing of those human rights to which this nation has always been committed and to which we are committed today at home and around the world.
Which way is time? Is time the tick of a clock? Is time motion? Does it flow like a river? And if it does, where does it go?
Discuss this.
Evidence of time, evidence of life, of a dark, bygone, unhuman past, of struggle, of survival, of evolution. Down through time I pass through rocks of ancient deserts, floodplains, and oceans. Probed through the mammoth units of geology. 200 million years ago, 300 million years ago, passed by walking only a few steps. I wonder, what is the significance of my life in these vast stretches of time? My mind can hardly comprehend the immensity of the figures. I saw here a distinctive sandstone formed from sand dunes of a great desert that 250 million years ago spread over vast areas of the American West. What forms of life, what kinds of plants, what insects could have lived in it? Footprints are all that remain. Time, my narrow view of the human scene. I and eternity. There were here in the Grand Canyon 2 great mountain ranges, perhaps as high as the Himalayas, that have come and gone. There were great oceans, great deserts like the Sahara, great floodplains like the Mississippi. All have come and gone. Now the place is a high plateau through which the Colorado River has cut one of the deepest gashes in the crust of the earth. When the river first started cutting, the age of man as an upright beast was still millions of years off. It seems so small, man's place in time, so unimportant. Near the bottom of the canyon and over a steep ledge lie rocks of shale, limestone, and quartzite, undisturbed relative to each other for eons of time. Jellyfish-like structures representing one of the oldest multicellular organisms known on Earth. 1,200 million years old, documents of a past, of time. But what is time? Is time life? Is it eons? Is time motion? The speed of light. Is it relative? Is it absolute? The light from Andromeda reaches the Earth after nearly 2 million years of travel. When it started, man was just beginning to claim the Earth. It is very old light, but it reaches me now. Past and present existing at the same instant in time. The dimensions of time, relativity, the past, the present, the future, the vastness of the universe, the place of man in time. There are footprints on the sands of time. The future is yet unwritten. What will man do with it? Whether he will survive or destroy himself is as awesome a question as that of time itself. Will time continue?
Woo! That was... I feel like I have another film about time that is also equally as just like, what is going on? Wow. This is our opportunity to take this concept and just... thank you, Encyclopedia Britannica, for that. And thank you for tuning in with us today. Today was a challenge, it sounds like, based on the comments, where we were going down one path where some people were happy, and we're going down another path and people were like, oh, that's crazy. And that's kind of the way it is. It's the roller coaster for your eyeballs. And I appreciate you being there for us. One of the ways that you can help us is by smashing the like button, or hitting the thumbs up button, or the like, or share, the subscribe, all those things that all those video podcasts that you watch that they talk about doing. Those are things that help us as well. You can also buy us coffee by going to ko-fi.com/avgeeks. You can also go to avgeeks.com and see other things that we put online, thousands of things. And also you can buy DVDs there. But thanks for joining us on today's bizarre adventure, visual adventure. And I hope to have more of these in the future. Because sometimes that's just the way it plays out. Some days it's really basic stuff, and some days it's like, woo! So thank you for being there for that. As always, we ask people to please rewind and to take care of themselves and love each other. And if they don't, there's the devil. So please rewind. And we will see you again tomorrow on Wednesday. Take care, everybody.